Hello, this is Mason Haggerty with question 7.35 from the Fundamentals of Heat and Mass Transfer, 8th edition. So in this question, there's a 1 meter long vertical copper tube of an inner diameter of 20 millimeters, wall thickness of 2 millimeters, containing liquid water at 0 degrees Celsius. On a winter day, there is wind blowing at 3 meters per second at a temperature of negative 20 degrees Celsius in cross flow over the tube. So first, we're supposed to determine the rate of heat loss per unit mass of the water in watts per kilogram when the tube is full of water. Then in part B, we're supposed to determine the heat loss from the water when the tube is half full. So I've listed the important constants here. So we have L equals 1 meter. The internal diameter, I converted to meters just for sake of calculation later, so I don't have to convert units. And you get 0.02 meters. Thickness 0.002 meters. And temperature of water is 273 Kelvin. The velocity of the air is 3 meters per second, and the T infinity is 253 Kelvin. So here's a cross-section of the tube. So we can see the thickness, the inner diameter, the cross-flow air, and again, just listing the useful dimensions. And I also calculated out here the volume internal and the volume external, so the copper tube included. And then here's a diagram of the pipe from the outside. Ignore that the water's sideways, but yeah, it's showing that it's half full, but I just drew it that way for ease. Okay, so our assumptions, we're going to assume steady state, constant properties, 1D heat transfer. The inner surface is the same temperature as the water, so that means that the copper tube inner surface is the same as the water. And we're neglecting heat transfer to the empty half of the tube, so the air in there, we're just assuming it's like a vacuum. Neglect radiation, and air at surface is average of air and water temperature, so the negative 20 degrees Celsius bulk temperature plus the 0 degree of water over 2, and gives us just, the average of 263 Kelvin. So first, we look at the tables. We're looking at copper at 300 Kelvin, which is from table A1. We're just assuming pure copper because we were not given any sort of alloy. So here's the screenshot of table A1. So the useful value from this for us right here is the K equals 401 watts per meter Kelvin. And along with this, we're going to go to table A4 and find air at 263. Unfortunately, the table does not have it at 263, so it has 250 and 300. You could probably just use 250 and be pretty accurate in your estimation, but I went ahead and interpolated all the values, and from that, I created this additional little table. So getting into analysis, we know that we want to find the Nusselt number because that equals the H times LC over K of F. And since we have the LC and the K of F, that will help us find our H. So for the Nusselt number for a tube of circular cross-section, we get the equation 7.54 from in the textbook of 0.3 plus 0.62 times Reynolds number to the 1/2 times Prandtl number to the 1/3 all over 1 plus 0.4 over Prandtl number to the 2/3 all to the power of 1/4 plus, or multiplied by 1 plus Reynolds number over 282,000 to the power of 5/8 all to the power of 4/5. So from the table, we have that the Prandtl number is 0.717, and the Reynolds number is going to be equal to the velocity of the air times the outer diameter of the tube all over the kinematic viscosity, which is, again, from the tables. So this gives us 3 meters per second times 0.024 meters over 12.6 times 10 to the negative 6 meters squared per second, which equals 5,714. Again, Reynolds numbers are dimensionless. So now that we have both the Prandtl number and the Reynolds number, we can plug it in, and you get this, which is 0.3 plus 0.62 times 5,714 to the power of 1/2 times 0.717 to the power of 1/3 all over 1 plus 0.4 divided by 0.717 to the power of 2/3 all to the power of 1/4 times 1 plus 5,714 over 282,000 to the power of 5/8 all to the power of 4/5, which equals 39.7136. So with this, you now know that the Nusselt number is equal to H times the characteristic length over Kf, which goes to It can be rearranged to H is equal to your Nusselt number times Kf over Lc. Your Nusselt number you now know is 39.7136, and your Kf is equal, again from the tables, is equal to 23.34 times 10 to the negative 3 watts per meter Kelvin, and your Lc is equal to 0.024 meters. From all this, you can again plug it in to find your H, and you find that your H is equal to 38.62 watts per meter squared Kelvin. So, from there, we're going to create a little thermal circuit. With this thermal circuit, we know that we have the water, there's going to be conduction through the pipe, and that will get to the tube surface where it will then convect into the air. So your R total is equal to the R conduction plus R convection. R conduction is the ln of R outside over R inside over 2 pi Lk. Again, this is for the tube, for a cylinder. So you get ln of 0.012 over 0.01 meters, and then you have that all over 2 pi times 1 meter times 401 watts per meter Kelvin, which is equal to your K for copper. This gets you 7.236 times 10 to the negative 5th. And then for convection, you have 1 over pi d outer times H, which equals 1 over pi times 0.024 times 38.62, which gets you 0.3434. So your R total is going to be those added together, and you're going to get 0.3435. And so to find your Q, you know that it's your delta T over your R total, which is equal to the temperature of water minus the temperature infinity over R total, which equals 0 Celsius minus negative 20 degrees Celsius over 0.3435, which equals 58.23 watts. So for part A, with M water equals the volume internal times rho of water, you're going to get a mass of pi over 10 kilograms by doing pi times 10 to the negative 4th meters cubed times 1,000 kilograms per cubic meter. And then the Q rate equals the Q over the mass. So you're going to get 58.23 watts over over 10 kilograms, which gets you 185.34 watts per kilogram H2O. And then for part B, you are supposed to assume that the empty half of the tube acts as a fin, which seems a little counterintuitive, but basically because you're conducting out of the water and then convecting around the tube, it does act as just a large fin. So for that equation, you get that the cube of the fin is equal to the square root of H times P times K times AC, all times theta B over MW. H is equal to 38.62 watts per meter squared Kelvin. Your P equals pi D, so that's like the perimeter of the tube. Your K is equal to 401 watts per meter Kelvin. Again, that's from the table for copper. Your AC, the cross-sectional area, is equal to pi times D outer squared minus D inner squared over 4. And your theta it will be equal to T water minus T infinity. And your mass of water is equal to pi over 20 kilogram. So for this, you get that the Q fin is equal to the square root of 38.62 watts per meter squared Kelvin times 0.024 meters times 400 watts per meter Kelvin, all times 0.024 meters squared minus 0.02 meters squared times pi squared over 4. Then you multiply all this by 0 minus negative 20 degrees Celsius over pi over 20 kilogram. And this gets you a Q fin equal to 51.15 watts per kilogram. And so for Q total, you have 185.34 plus so that's again from the per mass water, and then plus the fin. And so you get 185.34 plus 51.15 watts per kilogram, which gets you your total for part B as 236.5 watts per kilogram.